doing for this stuff. First, this is the primary right there, from small a to capital A. And this is secondary from small b to capital B. And remember, if currents are in the same direction, that's common. And if they're in different directions, that's differential. Right? So go ahead and tell me what's these things.
With terminals capital A, capital B connected, the impedance seen looking into terminals small a, small b.
Like this. Capital A, capital B, right? Well, here, if you look at the way current flows in this, that means current flows in this way and out this way, and that would be in the differential mode. Do you all agree with that, class? And if it's in the differential mode, then what we see is this. This impedance would be L minus M, this would be L minus M. I mean, excuse me, that would be the effective inductances, right? Are you all with me on here? And that means the impedance from here to here, from small a to b, Zn would be equal to really J omega times L minus M times 2. It's just twice the impedance of one of those windings, right? And he gives you a frequency of operations, 10 megahertz or a megahertz?
50.
Gives you a lot.
50 megahertz?
Yes.
All right, 50 megahertz. So now, that means omega is equal to 2 pi times 50, or it's 100 times 10 to the 6 pi, and that's radians per second, right? That's omega, and then he gives you Zn here, right? So he's going to say Zn is equal to J, and what does he give that value for?
300,000 at an angle of 90.
Yeah, and that's equal to J omega times L minus M times 2. Do you agree with that? So now we get L minus M. We take this and we can get rid of the J's. And so we have L minus M equal to 300,000 divided by 2 divided by omega, which is equal to really 10 to the 8 times pi. That's L minus M, correct? You can just leave it. I mean, you can give me the value if you want, but you don't have to. What did you get for this?
That's for omega.
You don't have to do it this way, but this is why I'm going to do it. While you guys are doing that, then the second way is second one is Zn would be equal to 2 times J omega times quantity L plus M. And what is that equal to?
10 to the 6th. 10 to the 6th. At an angle of 90.
Alright, so just J. So we cancel the J's basically right there. Now let's just see if maybe you don't need to do anything more than this. So if we have 2 omega L plus M equals 10 to the 6th, and the other one is 2 omega L minus M equals 3 times 10 to the 5th, right? For those two, you want to solve for L and M, correct? So if I take, it doesn't matter how you do this, but if you go ahead and say that L plus M is equal to 10 to the 6th over 2 omega, that means M would be equal to 10 to the 6 over 2 omega minus L. And then plug it into this one, so then you have 2 omega quantity L minus L minus quantity 10 to the 6 over 2 omega minus L equals 3 times 10 to the 5th. This is one way of doing it. If you take a look at this, what's going to happen is I can see I've got L plus L because it's minus this coin, so I have 2L here. And let me go ahead and just do that. So 2 omega times 2L minus 10 to the 6 over 2 omega equals 3 times 10 to the 5th. And from that point on, I multiply through by 2 omega, so I got 4 omega L is equal to 3 times 10 to the 5th, and then the 2 omegas cancel, and that's minus 10 to the 6, so it's plus 10 to the 6th here. And so L would be 300,000 plus a million divided by 4 omega. And you can tell me what you get for that, make sure the book's right. Y'all, I mean, there's several ways to do that. You can do it. You can just get L minus M there, then L minus M from the other one, and then just solve for one and then the other. But what do you get for this for L? So that's really what, 1.3 times 10 to the 6 over 4 times omega, which is 100, which is 10 to the 8th times pi. Can you give that to me, anyone? You got your calculator, so. Now I just put MathCAD on my on my laptop. If you got an open, you can do this in MathCAD a lot quicker.
It's about 1 million.
Anybody? Is that what it is? 1 million?
Yeah, it's like 1.035, but.
1.035 millihenries.
Yeah.
Once you have that, you can solve for L, or I'm going to solve for M just by, you can take this one and you can take, divide by 2 omega, subtract L from this. So M would be equal to 10 to the 6 over 2 omega, and then it's going to be minus L. And you can tell me what that is, because I don't know. I think everybody sees this, right? It's really just recognizing if you're in differential or common mode. And that's the whole game, and there's nothing tricky. What do you get for L?
For M?
Or M, I think?
0.56 millimeters.
I'm going to tell you, this is not as close as they usually are. Usually M and L are with a percent or two, maybe 3% difference. This is almost 50. I mean, it's a lot. And the reason they want it just about no difference is, so when you're in differential mode, the impedance is just about 0 for differential currents. You want them to pass. The only thing you're going to stop is common mode currents. Like if lightning gets a component on there or something like that, you don't want common mode current ever. And you probably heard about that in your electronics classes from whoever. I don't know if you've had, I don't know about digital electronics. Does he talk about common mode digital? Dr. What? Gofu knew? No? Well, who's teaching analog? Did you got Foster die? Huh? Did he talk about that? Common mode currents are bad. Any other questions? All right, so let us proceed into chapter 10. and this is microwave. Now I'm going to tell you something that's important about this. Keep in mind, microwave means virtually almost anything, from building microwave amplifiers to microwave links. When you get the way signals are routed, oftentimes you'll see these dish antennas mounted on the sides of things that look like cell towers, and they have a microwave dish there. They're just linking information to something maybe 10 miles away, 20 miles away, that's just through a microwave link. And then they use repeaters for that too. But microwave, first and foremost, you have to understand, usually most microwave design is done on things that are copper-cladded board where they delineate patterns. Now, this is a standard microwave, the side view of a board. You're gonna have just copper on top. And then you're gonna have a material with epsilon relative. It's called epsilon relative here. And this is a very low loss dielectric. And then you're gonna have another piece of copper on the bottom. So if you think about this, there's like a layer of copper here and a layer of copper here. And these boards are proportionally like this. They're flat, very thin, they got copper on back and front, all right? That's all it is. Looks like a parallel plate capacitor. Now what they do, if you're looking down at the top of the board, they're gonna delineate a pattern of something. Anywhere that they delineate the pattern, there's two types of this. There's positive and negative masks. What they do is they take the copper and they coat it with something called a photoresist. And then they harden the photoresist. First they make sure they spin the things usually, make sure it's evenly distributed. Then they dry it, so now they have a piece of material that's like film. It's called a photoresist. And then they delineate a pattern. And so if they want, for instance, a long line, they would allow everything to be removed except this line. So they would cut, if this was a positive resist, they would go ahead and cover that line with something that would shield it. And that's the photoresist with the mask. There's two ways. Did you all have VLSI fabrication? Yeah, have you had your fab courses? Well, the way they do all this stuff is, for silicon or anything where they're going to do any kind of etching to remove stuff, what they do is put a mask on there. And a mask is just something that is going to, I'm sorry. First they put photoresist on. And after they put photoresist, then they go ahead and they have a photolithography process, and it will delineate a pattern. Anything that's exposed to, if it's a positive resist, say an electron beam, that's going to be developed, and when they wash it in a solution, it'll come off. And the other stuff's left. Now the other stuff that's left is the stuff, like here what I'm saying is, I want just one copper line, so I want everything removed except for one copper line there, long. So what I do is after I put the photoresist on, and I spin it up and I dry it, then I expose all the mask except this part to something effectively like a light. But it could be electron beam, depends on how it's developed. And then I take that and I put it into a bath, usually it's a mild acid, and it takes off all the resist but the resist over the copper, all right? Then, now I've got the resist off, and I just have photoresist over this piece. Then I take that and I put it into an acid that will remove the copper. Follow me on this? But the acid can also eat away at the dielectric, so there's different types of chemistry involved in this. And then what you have is just this copper line. Now that's if I just wanted one line of copper. Typically when you're doing microwave engineering, this copper line here, with respect to the ground, is effectively the transmission line. That's it. And there's ways that you can do this to make this, they put guardrails around here, so what'll happen is my signal is going to be plus to ground here. Follow me? But I'm going to have a lot of signals, and I want to make sure that this signal, the plus to ground here, doesn't infect something else. So they'll let a line here and just ground that line, and this effectively shields the stray electromagnetic fields from getting over here to the other circuitry, all right? That's called that's just one method of doing it. And because they ground this line, effectively, all the signal that's on this line from here to here, it'll effectively either go to ground here, the electric fields, or here, and none of them will penetrate to this part of the circuit, anything on the other side. So that's the idea of this. And they'll put a guard line over here too, and these are copper. And here's my transmission line, one transmission line. This is not drawn to scale. There might be another, there's the guardrails here, the guardrails here, but you don't have to worry about that. Another transmission line. But what do you do with these transmission lines? Well, those are connecting to all sorts of electronics. You're gonna have amplifiers, you'll have mixers, things that are oscillators, and basically you build a very large circuit, something with maybe 1,000 transistors, maybe only 100 on something like that. That's a typical way microwave is done. And the board here, I'm just gonna tell you, I wish I had a piece down that I could bring with me. This is usually called Duroid board. Now there is something also called FR4 board, that's the green stuff. And this is green, but this has a high loss, this is high loss. So they'll use this maybe for 2.45 gigahertz signals, Wi-Fi, but they're not gonna use it for 50, 60 gigahertz signals because the losses per meter, or really per centimeter, in the FR, do you know what I'm talking about when I say FR4? Have you ever seen the green boards things are mounted on when you take them apart? Yeah, that is FR4 board. It's highly lossy, so you can get away with it if you're doing some microwave stuff around 2.45 gigahertz, but the minute you get up around, I'm guessing now 30 gigahertz for like KA band, forget it. You're not gonna use that, it's too lossy. This stuff's cheap, FR4. Maybe $1 a square foot, maybe 10 bucks, I'm not sure. Duroid board is at least $100 a square foot and up. It's expensive. So Duroid board is something you use when you need it, but you don't use it if you don't need it. And Dr. Wentworth does a lot of research, I think, or has in the past, using these board materials to build microwave circuitry. So that's basically what goes on in terms of the cross section. Now, a couple things you have to know. Usually, when they're designing this, write this down, I'm not gonna spend a lot of time on this. Usually what they do, this thickness of this copper is usually minimally important. It's a layer of copper that's primarily very thin. The width of this is important. And the height of this is important. And the value of the actual epsilon relative. Now on these things, I show you a piece of copper here, the bottom will always have copper. I say always, not always, there are exceptions, but usually the bottom is solid copper, it's ground. Now, here's something to think about. If I was to draw the field lines associated with this, and these are going to be, you've probably heard of how they do the trajectory of field lines. Like if you have a bar magnet, you see field lines with the arrows on the field lines, they're called, it's a contour. And if you look at the field lines for these, there would be one straight down here, then there would be some that fringe, and then you will get this coming, and basically the field in here is about vertically downward, usually. Now, the way they go about solving, if you were actually going to solve for the impedance of this, if the impedance, the characteristic impedance for this microwave strip, where there's a conductor and there's the ground, and there's a different epsilon relative here than there is above here, calculation can get involved. It's really something you need a computer for generally. It's not a closed form solution, I don't believe. But what they do, and I got involved in some of this years ago, what you do is take a computer simulation and you go ahead and you're going to show like this kind of thing. You're going to see, you remember characteristic impedance is equal to square root of L per meter over C per meter for a lossless line, right? Do you remember that? Well, now what they're going to do is calculate Z naught here for ratios of W to H, of width to height, for a given epsilon relative, right? And then they get something like this. As the width to height grows, the characteristic impedance goes down, down, down. I can tell you that. So then they take a different value of epsilon relative, and they'll get a different curve. And then a different value. And they develop what's something called a family of curves that represent how the characteristic impedance behaves versus the ratio of W to H. Do y'all follow me on this? But they actually get the values by doing a numerical simulation, actually a numerical solution to the problem, solving Maxwell's equations. Now, whenever you have a whole bunch of curves that are dependent on parameters, I got two parameters here, really the ratio of the parameters, and epsilon relative, now you can go into things like MATLAB and you can create, you want to look for what the constants are for some formulas to model that, to find a model that actually is a very good estimate of what those values will be for any given epsilon over relative and any given W to H. Do you follow me on this, guys? It's always the characteristic impedance, and when you design these things, you could care less usually about W of H, you care about this. You want to make sure that you match, impedance match everything. That's the critical thing. And where it becomes tough is when you get around the edges of the board. Then the characteristic impedance is harder and harder to predict. I did a journal paper years ago, probably about 25, 30 years ago, on how to take care of the edge affection. I had a whole family of curves and showed you what the functions were. What Dr. Whitworth's book does, he shows you some formulas that are based on curve fitting routines. And I'm not sure the page this is on your book, it's chapter 10. And what he does is starts with thickness T with W. That's the conductor here. I mean, that's copper down here. That's copper. This is H. This is epsilon relative. And the first thing he says, instead of using epsilon relative, they get an effective permittivity that accounts for the permittivity here and above. That's the first thing. So he's going to have epsilon effective, or I think it's EFF in his book. And that's equal to epsilon relative plus 1 over 2. And then I think in his book, there's different formulas for this. Then it's epsilon relative minus 1 over, and this one's going to be 2 times square root of 1 minus 12 H over W. You aren't expected to remember these things. I'm just got to do this for completeness, okay?
Yeah, plus 1 plus 12H.
I'm sorry, plus. Right. That should be plus. Now that's just an effective permittivity, and it's used in the characteristic impedance calculation, Z naught. But here again, this formula works for W over H. You can just look at it. W over H is less than 1, and this is a classic one. It's 60 over the square root of epsilon effective here times the natural log of 8H over W plus W over 4H, and I don't know why. This is more complicated than it needs to be, by the way. That's for W over H less than 1, for W over H greater than 1. Then you get a characteristic impedance that's equal to 125 over the square root of the effective. And then this is kind of a wild one, W over H plus 1.393 plus 0.667 times natural log of, and W over H plus 1.444. So that is needed to calculate these things. But frankly, this is the wrong way of doing business. Normally, what you want is you have W and over H, or sorry, you have a characteristic impedance that you want to develop. Suppose you're connecting this circuit to a 50 ohms input, right? You want the line to have 50 ohm. Almost all microwave cabling for test purposes is 50 ohm, almost all. So how do you get 50 ohms? Well, you don't do it this way and just keep on iterating, not trying to put it here and then calculate all this stuff. They have developed equations for that, and that's in the next pages. What they do is, they say, if you want a given characteristic impedance, he likes to do it this way. Oops. I don't even bother with this, but he's going to have like W over H equals 8 times e to the A, I think, in his, over e to the 2a minus 2, and this is an a, I forgot. What page is this on, by the way? I see that you.
547.
5 what?
47.
All right, now I'm just gonna tell you this. I don't expect you to memorize this or use this. What you have to understand is that value of A is buried in it. It's got the characteristic impedance you want if you're looking at it, right? So you can go ahead and find what the ratio is to W over H for a given epsilon relative, or epsilon effective. Do you all see that, class? Now, I'm not gonna spend time on this, but my real point here is just as exposure. These are nice for analysis, but almost nobody uses them. What they actually use is this, and there's 2 sets, and I wanted to tell you one other thing. Nowadays, you know how people do that? They simply have tools, they're online tools. You put in the characteristic impedance you want, you put in the epsilon relative of the dielectric, and pop, they tell you what WH to use. And so you don't even have to mess with this. You at least have to have an appreciation for where the equations come from. And all these equations come from assuming that it's in the TEM mode, but both electric field and magnetic field have no component in the direction of propagation of signal. Unlike waveguides, where things bounce down, you have E and an H field in the direction. This is all TEM propagation, and they just solve the simple del squared of V equation is 0, and they calculate with the value. They basically go through a numerical simulation to identify what the actual values of the characteristic impedance are. And these design equations, I believe, all come from just generating families of curves. Because you look at this right here, this did not come from Maxwell's equations. All this stuff came from curve fitting routines. And MATLAB has got a lot. And by the way, this and these equations that he has there, they're just one set. There are many, many sets of equations that govern that stuff. They're all pretty accurate. And if you ever get into having to design this stuff, just go online, go to Google or maybe YouTube, and just characteristic impedance design, microwave characteristic impedance design parameter stuff, and you'll see a whole bunch of stuff available. It's free. I believe there's a whole bunch of stuff. Now, I don't spend much time on that. One last thing, there's a maximum frequency that this can be used at before it stops acting like a waveguide, like a transmission line. And this is important to realize. Remember how when we had a coax cable that looked like this, right? At an inner core, and it developed a voltage V, and this is ground, and the field lines were like straight out. That would be the E field lines, right? Y'all remember that? And then the magnetic field was always like this. It was circulating. Now this is a transmission line. Y'all see that? However, as you keep increasing and increasing frequency, when you hit the point when from here to here you have a half wavelength, now that'll start behaving like a waveguide. And you won't have a mode with just a TEM excitation. Now you'll get a 1-0 mode. And you remember, the minute something has a second mode in it, the velocity of propagation changes. Do y'all know what I'm talking about? So that means you have a maximum frequency, even for the structures we talked about. When we have this kind of a structure where you have a top piece here, and then you have this as a bottom ground, right? Well, when this is about lambda over 2, and remember, lambda is a function of epsilon relative effective in the waveguide, then you go from a simple transmission line model to now it starts acting like a waveguide, and that's bad for business. So you have a maximum frequency. And in his book, he stipulates that as F max here is going to be equal to C over, and he has 4H times square root of epsilon relative. Now, really, if you want the truth, a good estimate is just with the epsilon relative in there. If that's lambda over 2, like I showed you, if H is equal to lambda over 2, and lambda is C divided by F divided by the square root of epsilon relative, over 2, then F max is equal to C over 2 square root of epsilon relative divided by H. Just trust me on this one. This is my, by the way, is this epsilon in this equation, is this effective or relative?
It's relative.
Okay.
545.
What he did was this. He's saying when this becomes a full wavelength, then it starts breaking down. But normally I have half wavelength. Anyway, this is a close estimate. Dr. Whitworth says that it's actually going to be this, and that's probably building in a safety mechanism, because what he's doing is, when he's using epsilon relative there, he's not getting the effective permittivity, the effects of effective permittivity involved. So instead of being just a half wavelength from here to here, that's going to be a quarter wavelength. That's probably based on a fair amount of research, so I would use that one. But remember, with these kind of things, you don't want to operate near that. Don't even get an order of magnitude close to it if you can help it. And that's fairly high if you think about it, because C is 3 times 10 to the 8th. H is going to be of the order of maybe, say, a couple of centimeters, right? So now you've got 3 times 10 to the 8th divided by, say, 10 to the minus 1 or so like that. So that's going to be 3 times 10 to the 9th, right? And then you're going to bring that's still only a gigahertz, and you're going to bring it down by the square root of this stuff. So you're near a gigahertz there for anything of the dimensions of centimeters. And I'm trying to think of how the thinnest FR4 board I've seen. Let's see. Maybe 5 millimeters or 6 millimeters. And if it's that thin, then you're up there to 50, 60 megahertz before you get to worry about it. Okay? Just remember that a lot of this stuff has to do with the thinner the board, the higher the frequency. Okay. Now that I've said that, and you can see I really am not going to quiz you on this stuff, you have to be aware of it. When you get your fabrication courses, you may get something involving this, but I'm really not sure. This is more for building things. The technical formulas that have to do with the actual fabrication. You haven't had your fabrication in the microelectronic fabrication lab yet, have you? No? It's still part of the curriculum, isn't it? Yeah, you get a microelectronic fabrication? Is it an elective you don't have to take it? I'd recommend you take it. For one reason, when you get out in the real world, see, especially if you guys go small company, almost always you're going to have to fabricate stuff yourself. Almost always. And if you're going to do any of the etching, any of the masking stuff, it's good to have done it at least one time in the past. Just like soldering or anything like that. You don't know, I don't know how much they taught you about soldering, but you don't use what? Acid core solder. There's lead core, acid core. Are you familiar with some of these things? You just are always given the right time. Well, you got to make sure you solder that's meant for, not for plumbing supplies or, for pipes and stuff like this. You want to use solder that's okay on electrical circuitry, that won't have any acid component that will cause the thing to basically erode over time. So now for the next part. Now we get into the actual microwave engineering, where we figure out the length of things we need, we figure out the value of components we need. Now you've done Smith chart stuff already before, where you did stub tuning, right? And you didn't do double stub tuning, and I'll talk about that if I have time later. But now we're going to take small components, and this happens all the time when you're building things and you want them on a, if you ever see some of these packages, look at your remote controls and stuff like this for your car key stuff. It's super small footprints that you gotta work with. So there they start putting in small little capacitors and things instead of long transmission, or long pieces of really effectively a transmission line, because they don't have the room for it. So here's how this works. First, we go ahead and we say how we want to match something. Suppose I have an impedance here on a microelectronic circuit, and now I want to impedance match it to something. And I got a characteristic impedance Z0 here for the actual microwave circuit. So here I've got something where I have a given H, I have a given W, a given thickness T, and a given epsilon relative. And all this stuff gives me a characteristic impedance Z0. But I have to connect something to this board outside of where the board exists, or on the board for that matter. And in connecting it, it has a ZL, and I want to impedance match it so there's no reflections, right? Well, here's what goes on. You know the impedance match, the first thing is you get the small ZL, and that's going to be equal to capital ZL over Z0. And a standard transmission line, or standard Smith chart, pardon me, has this. It has a 1 circle here. This is just 1 plus or minus JB there. Then it's going to have the standard J1 here and minus J1 here. Right? And that's what you're used to seeing. And the normal way to do this is, if it was ZL, you'd come in and find ZL, right? And if it was stub tuning in parallel, then you would go and find YL, right? And then you would move until you hit the 1 plus or minus JB circle. And then you would figure out the length of the stub that would have a value of, that would, when added to that, would negate the JB, right? Remember that? That's parallel, shunt stub. If it's series stub, you stay in the Z domain, you'd stay wherever you came in, and you move to the point where you have 1 plus JB. And then you would put a series stub that would have minus JB as its impedance, normalized impedance. Do y'all remember that? You'd be in the impedance domain. Well, now we're not going to add stubs at given lengths because it's probably at low frequencies. If you think about this, if you've got a wavelength of the order of a ½ meter and you want to go a third of that, you want to stub that long, well, that's a lot of real estate. You don't want to do that. So they use components to do it. And the way this is done, please understand, I'm going to try to do my best to make this as simple as possible. Draw a circle that's called a rotated circle here. It's identical to this one, but on the other side. All right. Now, if you look at this, those are the lines of constant J value, or minus J value, and there's always concentric circles of constant resistance, right? Do y'all remember how Smith chart goes? So here's how this works. The first possibility when you do this, start here, and the first possibility is that ZL is inside the 1 plus or minus JB circle. So it's inside this circle. This is the circle. Let me just show you how this works. So I'm going to assume it's inside there. I'm just going to put a dot there. Right? And just for the heck of it, let me pick up a value. So if that's inside there, that could be something like 2 plus J, and unfortunately I don't have a Smith chart in here, so 2 would be about there. Say 2 plus J1. Can you all see if that's inside the circle? The 2 definitely is, right? Is J1 inside here? Yeah, isn't it? Yeah. Okay. Now that's your ZL. That's normalized. But if it's inside there, this is what we do. Please just listen to me on this one. You'll see. There's nothing I can add to this that will move it up to the 1 circle. Do y'all see that? Because I've got a 2 here, and there's nothing I can do by adding in series, right, to get it there. I just can't. I'm stuck on this curve right here. But I can do something in parallel. Now, if I go from there and I go to the Y domain, and this is YL, which is 1 over ZL. By the way, what is the value of that? Can somebody just tell me? 1 over 2 plus J1? 0.1, this is 0.2. Anybody? I just need one over there.
0.4 minus J 0.2.
0.4 minus J 0.2. So that's your second point, right? Now, here's the deal on this one. I'm here, now I want to add something here in parallel. Now I'm in the Y domain, right? I want to add something in parallel, but here's what I want to do. I want to either have it come up, hope I can draw this right. You can see how there's a contour right here of a constant resistance, or a constant real value. Do you all see that, class? It's actually conductance. Well, if I'm at this point right here, can you all see how there's a line that goes straight up to here, right? Now, when I'm on that line, this 0.4 is where I'm at, all right? Please listen to this, this is important. I can add, I got minus 0.2 J. If I move up here on that line, if I go up the 0.4 line, I can hit a point where I'm right at this edge. Can I not, class? You're right. Look at it on that Smith chart I handed out to you. Where is that point? What is the value of J here? I need an approximation for this value of J. It's J. What is it?
0.5.
J 0.5. You all see, is that correct, class? So how far did I move? Well, I moved from minus 0.2 J to plus 0.5, right? Or 0.7. So I added a value in parallel of J 0.7. And he calls that B. Do you follow me on this, class? Y'all understand what I'm doing here? It's in parallel, it's Y. Right, we go from the Z domain, normalize Z to normalize Y. And then we add, and to add things in the Y domain, you add them in parallel, correct, class? So now I'm up here. Now the question is, what is this element? All right. And here I just make the case. If you think about a capacitor, that the capacitive impedance is 1 over J omega C. Does everybody agree with that? That's the impedance of the capacitor, period, at a given frequency, right? If it's the normalized impedance, then I would divide that by Z naught. And now I have the normalized impedance of the capacitor. Agreed? Now that's, call it Z normal of a capacitor. Now that means the normalized admittance, the Y, would be equal to 1 over that, 1 over Z normalized. And that's simply equal to J omega times C times Z naught. You all see that, class? I took the normalized impedance and I got a normalized admittance. You always use normalized admittance. Well, that means the value here of J 0.7 has to be equal to this, because when I put that element, that capacitor in the circuit, remember, it's the impedance we're using is normalized. So that means the impedances of the components, the capacitors, inductor, have to be normalized too, all right? So that means when I have that J 0.7 right there, that's equal to J omega C times Z naught. Let's assume I know Z naught, and I've got Z naught equal to 50 ohms, because that's happening all the time. So now I can see that the value of the capacitance can be gotten by just taking 0.7 over, and then it would be omega times Z naught. Now in Dr. Whitmore's book, he's going to leave this as B. I chose to give it actual values. That means that capacitance is 0.7 over 50, and now for omega. And I'm going to make F equal to 20 megahertz. So that means omega is 2 pi F, or it's 40 times 10 to the 6th pi, which tells me that this is 40 times 10 to the 6th times pi. And what do you get for a value here? about,
Is that 50 at the end?
this is 50 times 5 times 10 to the 6 times 40.
I got 11 nano.
Is that right? 11 times 10 to the minus 9, is that right?
Yes, sir.
Alright, so it's 11 times 10 to the minus 9th, and that would be farads. Alright, so it's 11 nanofarads, which is very small, but nevertheless, it's available. And I'm going to tell you one other thing. If you're going to do this, you need to make sure the lead links are as short as possible, because they're a problem. So that's the capacitor. Now, I'm right at this point right here, and now I'm at a point where I've got my Y value here is going to be 0.4, and it's going to be plus J 0.5. And that's point, let's see, 1, 2, this is 0.3. You all see that, class? Started here in the Z domain, jumped to the Y domain, then moved to this point, and I saw how much more, how much B, you could say, how much JB that I have to add in parallel with it. Follow me? Now I'm here, take 1 over that and tell me where I'm at. There better be a 1. This would be the 4th point. What are you getting for that?
Going from where now?
I'm in the admittance domain, and I'm at the point, when I add that element, that J7 on there, 0.7, then I have 0.4 plus J0.5, right?
Yes, sir.
Now, take that and do 1 over that. Because I want to get back to the impedance domain. This is admittance, this is impedance, correct? Hey, you better give me a 1 first, or something very close to 1 plus 7. What do you get?
Yeah, it's like 0.97, 0.98.
Alright, we're going to call it 1 plus J what?
1 minus J 1.22.
Minus J 1.22, is that right?
Yes, sir.
1.22. Alright, now, that means that this impedance, that 0.4, that's, call it Z normalized 2, and that's what I'm seeing right here, right? I've got that impedance, Z normalized 2, right? Now, I want the impedance, normalized impedance for impedance matching purposes, to just be 1. Right? So now I've got to get rid of this minus J 1.2, and it's got to be normalized. Well, what has a value, an impedance of a plus J value to it? Because it's got to be a plus J, right? When we add them in series, we're going to add this one in series. It has to be an inductor, right? An inductor has an impedance of J omega L, normalized as J omega L over Z naught, and that has to be equal to 1.22. So now I can say that 1.22 is equal to J, I'm going to get rid of the J omega times L divided by Z naught. You'll notice I'm always taking and I'm normalizing the impedances. Now I can find L, and L will be equal to 1.22 times Z naught, right? And then it's going to be divided by omega, which is really 40 times 10 to the 6th times pi. And that's the value of the inductance. What do you get for that? Then we'll go see. Follow me what I'm doing here?
What is Z naught?
Z naught I put is 50 ohms.
50, okay.
And I just made it typical.
It's like 3.1 micro.
Anybody else? Microhenries? 3.1
Yes.
did you say?
3.1.
Okay. 3.1 microhenries. Anybody else?
I got
Oh, no, I didn't do 2 pi.
I got 0.5 micro.
That looks right. 0.5 microhenries. Okay.
Yeah.
So the circuit itself, I mean, just the lump elements would look like this. You would have your load right here. Then It's normalized load right there. Then I would have a value of a capacitor here that we calculated, and an inductor here, and then I would be impedance matched from that point on. The benefit of this, let me finish this, is that this can be at a very small footprint. You can put in elements L and C without using much real estate, much space. Whereas if you're using stub tuning, right, those stubs can be long, and that can take a lot of real estate. So especially at lower frequencies, you want to use components. Go ahead.
I was just gonna say, for that capacitor, I accidentally calculated it wrong. It's actually 0.11 nano.
Okay. 0.11.
Yes, sir.
Nanofarads. So it's 110 picofarads. That's small, but it's still available. You can get picofarad capacitors, and if you use them, trim the leads way down, because those things, the leads cause a lot of problems. So that's how you do it. Do this if you want to use components to do the impedance matching, if it's in here, right? If ZL is inside the one circle. Now, the second case is going to be if it's inside the rotated circle. I always ask about the weather in the afternoon classes. Yesterday I was here and looked at the weather. It says no chance of thunderstorms. What a lie. Went to the rec center. I'm there, raining like crazy, everything like that. And so I learned in Alabama that if you don't like the weather, wait a half hour to change. And I don't know if we're scheduled to get rain or not this afternoon.
Just 20% chance.
Okay. I wonder how long that was. So now, you can see I'm naturally suspicious because I get rained on a lot, and I don't take my umbrella up because I believe these guys. And I realize that their confidence interval must be like somewhere of the order of 50%. And they say chance of rain 20%. What does that mean? In a full hour, it's 20%. Probably at that point in time, it's a 1 in 5 shot you're going to get rain, right? But how they figure that out is beyond me, because they never have explained that to me. And frankly, I think sometimes they just
Don't make it up.
Huh?
They just make it up half the time.
Hey, look, it's clear, no chance. All right, well, I know there's a lot to meteorology, and I know they're accurate to some extent, but predicting the weather down here in Alabama, it's like trying to predict if it's gonna be heads or tails on a coin. Because it's tough. All right, now for this one, this is the second part. Now, ZL is inside the rotated circle. So I'm going to just pick a value inside the rotated circle. Let's say its ZL is 0.4 minus J 0.2. That's about where we were last time, isn't it?
Yeah.
0.4 plus J. Now remember that's Z, right? So I'll draw my circuit over here. This is ZL. And I know the normalized value of ZL is 0.4 minus J 0.2. And now I want to add something to this. I want to work in the Z domain. Now you know that there's this big circle, and this is the 0.4 real circle here, right? Please watch this, make sure you see this. Now what I'm going to do is the same thing as I did before. And by the way, I can go down this way too. But if I'm doing impedances, if I want to add positive J impedance, I go this way. If I go from here to here, this better be about 0.4 plus J 0.5, isn't that right? Right. If I go this way, I'm going to add 0.7, right? 0.7, it would be positive 0.7 J, right?
Yeah.
Well, that would be an inductor, a normalized inductance. If I go down this way, and I'd be subtracting, I would go to 0.4 minus J.5, then I'd be adding a capacitance here. You follow me? But there's no saying, nobody's limiting you to go this way versus this way. I choose to go this way just because I do, for no other reason than I did before. So if I go up to this point, now I move the distance of 0.7 J, right? So this total delta here, delta movement, delta B, really JB, is going to be 0.7 J, correct? But it's in series this time. So now I put down J 0.7, but that's a normalized impedance. And that means this is going to be realized with an inductor. Y'all with me? And the way you get it is, first you start with the reactance of the inductor, and that's going to be J omega L. That is ZL, or that's the impedance of an inductor. Then you normalize it, divided by Z naught. And now you set it equal to that value, J 0.7. So you can see the value of the inductance is going to be 0.7 times Z naught divided by omega. There's the value of the inductance you'd get. You all see this? But it's in series, not in parallel. So when you're in a rotated circle, your first move is going to be a series element. Now, when I jump from here to here, I get 1 minus J, you know, and that one again. We just did this.
1.22.
1.22, right? Now here, I've got, and now I'm in the admittance domain, correct?
Right.
I want to add an admittance to get rid of it. So I want to add an admittance here of plus J 1.22. And then I'm impedance match, correct, class? Well, if I'm here and I want to add plus J 1.22 to it, so if this added with this would just give me 1, right? Everybody with me? I can say first capacitive reactance, Z capacitive is 1 over J omega C. Normalized capacitive reactance is this. And that means capacitive admittance normalized, Y subcapacitive normalized, is going to be J omega C times Z naught. Correct, class? This is the second time we've done this normalization. Correct, everyone? Now, this has to be equal to the actual value of J 1.22. So now I say J 1.22 here is equal to J omega times C Z naught. And I can find out the value of C, get rid of the J's, C by taking 1.22 divided by omega Z naught. And I don't need to put in the Z naught and omega for this one. I think you know how to do that, right? But here we've done one where we went series first and then shunt parallel, okay? Before it was shunt parallel, then series. Now this is for the rotating. Finally, if it is outside both, then you can do either. It doesn't matter which one you do first, but you have to know which domain you're working with. So we're going to pick one of those values and do this. So now we do this. This is the 1 plus JB circle, and this is the rotated circle, 1 plus JB rotated circle. So now suppose your point's outside of both. Help me out here and tell me if I'm right. So I know this is the J1 line right here. So if this is 1, suppose I'm at 0.5 plus J1. Can you all see that point? Right? Can you all see that?
Plus J1.
Yeah, plus 0.5 plus J1. You should be able to see it.
Yeah.
Yes, sir.
Now, what this 0.5 tells me is that is the real part, so it goes something like this. And you're always gonna look at the real component. That will not change at all with this one. So you can do this a couple of ways, and I wanna show you how. All right, well, let me show you a way. What I can do is I've got J here. I can move from there until I hit this point. Now that would be adding impedance in series. Do y'all see that? This is the impedance domain. We would add J until, excuse me. Ooh, I'm sorry, we would subtract J. That's positive J would be subtracting until we got to this point. So it'd be from 1 to 2. All right, now just listen to me, we'll do the numbers in a second. Y'all see what I'm doing here? Yeah. Now at that point, I'm on the rim of this circle, which means I'm on the rim of that circle if I go to the other domain. Now I go to the admittance domain. There's my third point. And now, right here, now I have a Y, right, of 1 plus or minus J something, right? This is going to be subtracting impedance, really, it's going to be a capacitor in series. It's going to take it down to this point, and then I'm going to move here, and once I'm here, I'm in the admittance domain. So if it's a minus admittance and I want to get rid of it, I put a capacitor. Correct, class? Help me out and see if you can get this one. Where does this land? On the 0.51, where does it intersect the one circle?
0.5 plus J 0.5.
Yeah.
Plus J what?
0.5.
0.5? Oh, good. So that means I just got J.5 to subtract from it, right?
Yeah.
All right, so now, for this one, it's looking like this. I have ZL here. Now, the first thing I'm doing is going to put a capacitor in series with it. And I know that first, for the capacitor reactance, it's equal to 1 over J omega C. Therefore, when I normalize this by Z naught, it's this. And that would be small zc. And then YC, or the normalized admittance of a capacitor, would be J omega C times Z naught. That's this. And I want that to be equal to 0.5, right? Because the capacitor I'm sorry. Did that wrong. Here is what I want. My bad. This is impedance first. I'm sorry about this. So this is really equal to minus J over omega C Z naught. And that has to be equal to 0.5 because we went from J1 to J.5, or we need to subtract J.5 from it. So here we say minus J 0.5 is equal to minus J omega C Z naught, or we get rid of the minus J's and we say that C here would be equal to 1 over 0.5 right there. Then it's going to be omega Z naught. Can you all see that, class? And now I'm right here. And what is this value? 1 over 0.5 plus J, this looks like 2 plus J2. I'm not sure. What it can't be, it's got to be 1 plus J1, isn't it? Or 1 minus J1. Is 0.5 plus J.5 over 1 equal to 1 minus J1? All right, so now I've got 1 minus J1. I'm in the admittance domain. I need to add an admittance of plus J1. Do you agree with that, class? And what is that going to be? That's another capacitor, isn't it? Correct, class?
Yes.
And here, then we do this right here. We go to that calculation and we say, since it's equal to 1, we just say J1 here would be equal to 1 over no, this would actually be equal to J1 be equal to omega C Z naught times J, or that C would be equal to 1 over omega Z naught. Do you all see that? Are you with me on this, class? What I'm really trying to tell you is that there's gonna be a couple ways we could do this, but y'all see that adding series brings you to the one circles, either the rotated or the actual circles. You with me? Either the 1 plus JB's actual circle, the one circle, or the rotated circle. Once you're on either one of those, you hop to the other domain by going right through the center and taking 1 over that. And then you add an element to there, either in parallel or series, that'll get rid of it, right? Now here's the other way to do this problem. I'm here, and I started in the impedance domain, right? Well, what if I jump from here to the admittance domain? Now, if I'm in the admittance domain, I'm going to add a certain admittance so that I get to the rotated circle here. Follow me? Can you all see what I'm doing here, guys? It would be in parallel, in other words. I'm adding an admittance, but I'm going to stay on that R constant line, whatever it is, right? Add an admittance. If it's positive, it's a capacitor. If it's negative, it's an inductor, right? If it's in the admittance domain. I move here. Now I'm on this rotated circle, so I know when I go to the other domain, first it's shunt, and then I go in series. Now this is the impedance domain, right? Now I'm at 1 plus J something, right? And now to get rid of that, I add another capacitor, correct? Or I'm going to get rid of that by just, if it's 1 plus J something in the admittance, no, the impedance domain, then I add a capacitor in series with it, correct, class? But that's the idea. Do you follow me on this stuff? So there are 3 possibilities when you do design work using Smith charts with components. One is if it's inside the rotated circle, you always have to put something in parallel. If it's, inside the actual circle, the one circle, you have to put something in parallel. If it's inside the rotated circle, you have to put something in series. And if it's outside either of those circles, you can do whatever you want. It doesn't matter if you're working admittance first, then impedance, or impedance, then admittance, okay? And that's the basics of this, and I try to make it as easy as possible. Now, on the remaining time, I'll tell you that Monday's our test, is that right? Yes. Okay. All right. We're going to get into something called scattering parameters, and this is typical of microwave engineering. I'm just going to just give you a little taste of what we're up to. Scattering parameters really have to do with systems that are called two-port systems, and it relates input to output in these systems. Let me explain something to you. Usually when you have microwave amplifiers, what you're going to have is an input. You're going to have a coax in, or a transmission line in, and transmission line out. And the circuit itself may be just a module you buy. I mean, you can fab it, there's nothing against that, but usually they're modular. And what they do is this. They're going to have something where they have a box here, and they're going to have, this is just a standard 2-port. This is port 1, and this is port 2. And then, in here, this is going to be plus to minus V1, and this is plus to minus V2, as such, and I got to see if, I'm just checking one thing here. There it is. Diagram on page 559 is what I'm after. But here's how it's actually looked upon. Instead of putting V1 and V2 like that, what they're going to do is say at port 1 you're going to have a positive going voltage. You're going to have V1 plus, and that's going into the port, but so you're also going to have a reflective voltage here, and that's V1 minus. In this port, you're going to have something going into the port, and that's V2 plus, and you're also going to have something coming out of the port, that's V2 minus. Y'all follow me in this class? Now the way he sets it up, the things that relate these two, in his thing, is generally they put a block V bar equals S double bar times V, this is V1, V2 bar. And And again, I want to say, this is just 2 ports, but you could have any number of lines here. And now they're going to have V1, not the way he does it in his book. Sorry. Get rid of that. 2. This is going to be V1 minus V2 minus. It's going to be equal to an S11, S22, S21, S12. And then he's going to have times V1 plus V2 plus. Oh, he does have the negative and positive, not 1 and 2 on 1120. You could have as many as you want here. And this is always going to be a square matrix in the thing that links them. So this says this is the voltages into the port that are coming in. These are the voltages leaving the port. Now, there's a standard thing. When you think about reflection coefficient on port 1, reflection coefficient is always going to be V1 minus over V1 plus, right? That's what the definition of reflection coefficient is. That's on port 1. Reflection coefficient on port 2 is going to be V2 minus over V2 plus, right? So if you look at this, V1 minus over V1 plus, well, when I take this times this, I get V1 minus is equal to S11 V1 plus S12 V2 plus, right? And what is the ratio of V1 minus over V1 plus? That's this, is it? Take a look at that. You can say setting V2 to 0 if you want. This is going to be, if you look at that, that's V1 minus over V1 plus, assuming V2 plus equals 0, or there's nothing driving the port, the second port. Right. That's the reflection coefficient. So S11 is really the reflection coefficient of port 1. S22 is the reflection coefficient of port 2. Now, the cross terms 2-1 and 1-2 are called the transmission, or they're really, they're the gain, and I'm going to get it, I'm out of time right now, but they have to do with the gain. This one and this one have to do with like the amplifier's characteristic, how much gain you have, and they're functions of frequency. I'll get into that later, and I'll try as best I can to make this as applicable as possible. If I can, I'll get some drawing board and show you what I'm talking about, maybe even with some circuits. But with small businesses, when you guys are designing stuff, and some of you here probably will be, you're going to be doing S-parameter design stuff. I didn't give you a quiz last week. Can you guys forego a quiz? And just that way we can do for the test on Friday? You okay with that? Just show up because I want to make sure I get to cover all the material. All right, guys. Oh, why am I so tired? I feel like I'm running out of fumes.